So welcome to lecture 3 of dual nature of radiation and matter. So we are beginning with the problems based on the concept which we have come across. So we are dealing with the first problem. The work function of cesium metal is 2.14 electron volt when light of frequency 6 into 10 to the power 14 hertz is incident on the metal surface. The photo emission of electron occurs. What is the maximum kinetic energy of the emitted electrons, the value of stopping potential, and the maximum speed of the emitted photoelectrons? So if we consider this particular problem, we have the value of work function that is given as 2.14 electron volt. The value of incident frequency of light is equal to 6 into 10 to the power 14 hertz. So if we calculate the incident energy, then we can say that incident energy is equal to h mu, where h is the value of Planck constant. So if I put the value that is 6.63 into 10 to the power minus 34, this is the value of Planck constant in SI unit, into 6 into 10 to the power 14. So the value will be in joule, and it is turning out to be 3.98 into 10 to the power minus 19 joule. So we can convert this energy in joule in electron volt by using a simple expression. 1 electron volt is 1.6 into 10 to the power minus 19 joule, and hence we can convert this expression in joule in electron volt by dividing it by 1.6 into 10 to the power minus 19. So the value will be in electron volt, and we are attaining a value that is equal to 2.487 electron volt. So we get a value like this. Now if we calculate the maximum kinetic energy of the emitted electron, so I can say that kinetic energy maximum is equal to incident energy minus work function. So the value of incident energy is equal to 2.487 minus 2.14 in electron volt. So I can say that the maximum value of kinetic energy of the emitted photoelectron is turning out to be 0.347 electron volt. So if I talk about the stopping potential, then if this is the maximum value of kinetic energy with which the electron is emitted, so the stopping potential must be equal to 0.347 volt in the opposite sense, so that the electron will get retarded before reaching the receiver plate. Then the next part, the problem is asking maximum speed of the emitted photoelectron. So we are equating the value of kinetic energy with a half mv square. That is, I can say that kinetic energy which was half mv maximum square is equal to the maximum value of kinetic energy of the emitted photoelectron. And over here I can write it as half of 9.1 10 to the power minus 31 V maximum square, and it is equated to maximum value of kinetic energy, that is 0.347 into 1.6 into 10 to the power minus 19 in joule. So we have converted the value in joule. So from here we calculate the maximum value of speed, that is 2 into 0.347 into 1.6 into 10 to the power minus 19 upon 9.1 10 to the power minus 31 square root. So the value over here is turning out to be 0.349 into 10 to the power 6 meter per second, which we can write it as 349 kilometer per second. So these two are the possible answer for this particular problem, that is the maximum speed of the emitted photoelectron. Let us move to the next problem. The next problem is stating monochromatic light of wavelength 632.8 nanometer is produced by a helium neon laser. The power emitted is 9.42 milliwatt. Find the energy and momentum of each photon in the light beam. The next part is how many photons per second on the average arrive at a target irradiated by this beam. Assume the beam to have a uniform cross section which is less than the target area. And the last part, how fast does a hydrogen atom have to travel in order to have the same momentum as that of the photon. So if we begin dealing with this problem, so over here the wavelength that is given to us is equal to 632.8 nanometer. 632.8 nanometer, and the value of power, so I'm writing in full power, that is we are symbolizing it with capital P. It is 9.42 milliwatt, that is 9.42 into 10 to the power of minus 3 watt. So over here we are using the formulation that incident energy EI is equal to hc by lambda, and I can write it in this way: 1240 by the lambda in nanometer will give us the value of energy in electron volt, and this expression is very important for us to calculate the value directly in electron volt. So if we do this, so we can write that the value of incident energy is equal to 1240 divided by the lambda, that is 632.8 in nanometer, and the value is obtained in electron volt, that is equal to 1.96 electron volt, or I can convert it in joule, that is 1.96 into 1.6 into 10 to the power of minus 19 joule. So the value over here is coming out to be 3.14 into 10 to the power minus 19 joule. So this is the value of the energy of each photon in the light beam. Now in the next part we are going to discuss about the momentum. So if I write the value of momentum, so we study momentum P. I am writing this as small p over here, is equal to h by lambda. So if I write momentum as h by lambda, so we can write it as 6.6 into 10 to the power minus 34 upon the wavelength, that is 632.8. It is in nanometer, we are converting it in meter, and the value will be in kg meter per second. So over here we attain a value equal to 1.05 into 10 to the power minus 27 kg meter per second. So this is the momentum of each photon in the light beam. Now in the next part the problem is asking how many photons per second on the average arrive at a target irradiated by this beam. So if I consider it in this way, for a beam of uniform cross section which is less than the target area, so I can say that if n is the number of photons striking per second, number of photons is striking per second, then I can write that power is equal to E into N, where E is energy associated with each photon. So, and then we get this value of power P. And now if I write the value of N, that is the number of photons that is striking per second, then we can write it as P by E. The value of power is given to us as 9.42 into 10 to the power of minus 3 watt divided by the value of energy, that is 3.14 into 10 to the power minus 19. So we attain a value equal to 3 into 10 to the power 16 photons per second. So this is the number of photons that is striking per second. In the last part the problem is asking how fast does a hydrogen atom have to travel in order to have the same momentum as that of the photon. So in order to acquire the same momentum as that of the photon, so we are solving the last part or the C part. So we are writing the mass of hydrogen atom, one hydrogen atom, so we will not write H2, we will just write MH. So mass of hydrogen atom is taken as 1.6 into 10 to the power minus 27 kg. and if it is traveling with a speed v, then I can write that momentum p is equal to mv, and v can be written as p by m. So the value of momentum is calculated as 1.05 into 10 to the power minus 27 divided by 1.6 into 10 to the power minus 27, and from here we attain a value that is equal to 0.66 meter per second. So this is the speed with which the hydrogen atom must be moving in order to acquire the same momentum as that of a photon. So let us deal with the next problem. The next problem is stating the energy flux of sunlight reaching the surface of earth is 1.388 into 10 to the power 3 watt per meter square. How many photons per square meter are incident on the earth per second? Assume that the photons in the sunlight have an average wavelength of 550 nanometer. So if we begin this particular problem, we state writing the value of energy flux which is given in the problem. So the value of energy flux that is given to us is equal to 1.388 into 10 to the power 3 watt per meter square. It can also be considered as the energy incident per second per unit area, the value of energy flux that is mentioned. And we are considering that the value of average wavelength of the light that is incident is 550 nanometer. So if I calculate the energy corresponding to this, then we are writing it as 1240 by lambda in nanometer, and the value will give us the value in electron volt. So it is coming out to be 2.25 electron volt. So I can convert this in joule. So 2.25 into 1.6 into 10 to the power minus 19 joule, and we attain a value that is equal to 3.6 into 10 to the power minus 19 joule. So this is the value of energy of each photon. So now we are considering that let n be the number of photons, be the number of photons striking per second per meter square. So n is the number of photons striking per second per meter square. So the value of energy flux can be written as the value of energy of each photon into total value capital N. So now the value of this flux phi is 1.388 into 10 to the power of 3 upon 3.6 into 10 to the power minus 19 will give us the value of n, and from here we calculate this as equal to 0.385 into 10 to the power 22, or n can be written as 3.9 into 10 to the power 21 photons per meter square per second. So this is the answer for this particular problem. We are dealing with one very interesting problem now. So we are dealing with the next one. Light of intensity 10 to the power minus 5 watt per meter square falls on a sodium photocell of surface area 2 centimeter square. Assuming that the top 5 layers of the sodium absorb the incident energy, estimate the time required for photoelectric emission in the wave picture of radiation. The work function of the metal is given to be 2 electron volt. What is the implication of your answer? So if we begin dealing with this particular problem, so we are beginning by considering one assumption. So the assumption which we are taking over here is we are assuming one conduction electron per atom. So I am writing assumption. We are considering one conduction electron per atom, and the next thing is effective atomic area effective atomic area to be 10 to the power minus 20 meters square. So what we are considering is that the radius of an atom is approximately 10 to the power minus 10 meter. So if I just square it out, we are considering that the uh, approximate effective atomic area is 10 to the power minus 20 meters square. So the next thing that we discuss is number of electrons in 5 layer. So over here the problem stated that assuming that the top 5 layers of sodium absorb the incident energy. So I am writing number of electrons in top 5 layers. Number of electrons in 5 layers. So we write it as 5 into the area of the patch that is given to us as 2 centimeter square. So we write it as 2 by 100 that is 2 into 10 to the power minus 4 meter square divided by the effective area that is 10 to the power minus 20. So it is giving us the value that is equal to 10 to the power of 17. So the number of electrons in the 5 layers is of the order of 10 to the power 17, and the value of incident power can be calculated as the intensity into area. So the value of intensity is given to us as 10 to the power minus 5 watt per meter square into area, that is 2 by 10 to the power 4, and the value will be in watt. So it is turning out to be 2 into 10 to the power minus 9 watt. So the incident power can be written as 2 into 10 to the power minus 9 watt, and the total number of electrons in this region is 10 to the power 17. So now we are considering that according to the wave picture, the incident power is uniformly absorbed by all the electrons continuously, and I can say that the energy absorbed per second per electron, energy absorbed per second per electron can be calculated as 2 into 10 to the power minus 9, which was the power, and the total number of electron, that is 10 to the power of 17. So we attain a value that is equal to 2 into 10 to the power of minus 26 watt. So this is the value of energy absorbed per second per electron. We are considering the wave picture, that is wave analysis is done, that is the incident power is uniformly absorbed by all the electrons continuously. So now if I calculate the time required for photoelectric emission, the time required for photoelectric emission, we are given that the value of work function is equal to 2 electron volt. So 2 electron volt can be written as 2 into 1.6 into 10 to the power minus 19 in joule, divided by the value that we ascertained, 2 into 10 to the power minus 26, and the value is coming out to be 1.6 into 10 to the power 7 second. Now this is a huge time, and if I divide this by this, that one day, if I write, then one day is equal to, it is 86400 second. So if I calculate in days, so I can write 1.6 10 to the power 7 upon 86400 days, and we get this value as 185.185 days. It is approximately half year. Now over here we prove, or we can rather say, that the experimentally the photoelectric emission is observed nearly instantaneously. When I say nearly instantaneously, I mean to say that the time lag between the incidence of photons and the emission of photoelectron is of the order of 10 to the power minus 9 second, that is nanosecond. This is the time that it takes, and thus the wave picture is in disagreement with the experiment. So they are not together, they are not complying with each other. In the photon picture, energy of the radiation is not continuously shared by all the electrons in the top layers. Rather, energy comes in discontinuous quanta and absorption of energy does not take place gradually. So as a result of which over here I can say that wave picture is not the correct analysis for the photoelectric effect or the photoelectric emission, and hence we consider that photoelectric emission is an example of a particle nature of light. So with this we can say that the photoelectric effect thus gave us the evidence to the strange fact that light in interaction with matter behaved as if it is made up of quanta or packets of energy, each having energy h mu. But then also over here we have established the particle nature of light. So when I say the particle nature of light, which we refer to as photon, so we are summarizing the following picture of photon in electromagnetic radiation. So the first point that we need to summarize over here is that it interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. So we are referring to particles called photons when we talk about radiation. The next one is each photon consists of energy that is given by E equal to h mu or h c by lambda. So each photon consists of energy packet that is E equal to h mu or h c by lambda, where c is the speed of light and mu is the frequency of the incident electromagnetic wave. The next point which we say is the photons are electrically neutral. They are electrically neutral and hence are not deflected by electric and magnetic field, and hence are not deflected by electric and magnetic field. And the fourth point which I am mentioning over here is in a photon particle collision. So in case of a collision, that is in case of a photon particle collision that is taking place, the total energy and the total momentum are conserved. The total energy and total momentum are conserved. So these are the points which must be very well kept in mind as far as the nature of photons are concerned. Now we are talking about, as we have stated, the dual nature of radiation and matter. So now we are talking about the wave particle duality, or we will be beginning to study about the fact what is the true nature of light. So when I say the true nature of light, there is no one correct answer for this particular part, because in 1801 Young's double slit experiment was performed, and it was shown that the light exhibit fundamental properties like a wave, and then followed by this the diffraction and interference was also observed. Based on this, several years after this, Maxwell discovered that light was a wave of oscillation of electric and magnetic field, which we have already dealt in chapter known as electromagnetic waves. So there is a lot of confusion regarding the nature of light, and over here we are beginning to understand de Broglie's hypothesis. So this is pronounced as de Broglie, but we write it as de Broglie's hypothesis. So now if I tell you the history behind it, so in the year 1923, as a graduate student, Louis D. Broglie or Louis D. Broglie made a surprising suggestion which was later confirmed in 1927 by different experiments. And what was the experimentation all about? The experimentation was about the fact that there is a wave particle duality. When I say the wave particle duality, then I mean to say that he said that the light behaves like a particle, a stream of photons, and the wavelength of light is related in such a way that we write that lambda is equal to h by p, where p is regarded as the momentum of the photon, where p is regarded as or called as the momentum of the photon, and hence we can write it as, for a particle of mass m, I can replace it with h upon mv. So we can replace it as h upon mv, and hence we can also write it in terms of momentum p can also be written as h by lambda. So this is the momentum equation for a light or photon with wavelength lambda, with wavelength lambda. The next thing that we discuss over here is various possibilities in which this equation can be written. So I can write that lambda is equal to h by p. We can write it as h upon mv. We can also write it as h upon root over 2m of kinetic energy. So these are the various possibilities in which we can frame or write this particular equation. So if we consider an electron having a mass m and charge e, which is accelerated from rest. So we are taking the example of a for electron. So for electron we are considering that it is having a mass m and charge e, and accelerated from rest through a potential difference v. Accelerated through potential difference v. So the kinetic energy of the electron will be equal to, so I can write, hence the kinetic energy on accelerating through v can be written as ev, and I can say that this value of kinetic energy, which is equal to half mv square, can also be equated to p square by 2m, where p is momentum, or we come to this fact that p is equal to root over 2m kinetic energy, which we have already used in the previous expression, or we can write that 2m ev. Based on the equation of kinetic energy, which is equal to ev, we can write p equals root over 2m ev, and hence we can say that the Broglie wavelength lambda b for the electron can be written as h by p, which is equal to h upon root over 2m ev. So if we look at this expression, then h, m and e are constant along with 2. So the value of this expression is written as 1.227 by root over v in nanometer, where v must be in volt. So if we fix the potential difference or the accelerating potential in volt, then we attain that the value of wavelength lambda is equal to 1.227 by root over v. So this is the value of Broglie wavelength of the equation, which we can use for directly calculating the Broglie wavelength for electron. Now later on, this Broglie's wavelength was, or Broglie's hypothesis was formulated or used by Bohr to explain the atomic structure. That is, he stated that he used this while stating the angular momentum, or his second postulate, where he said that mvr is equal to nh upon 2 pi. So we will discuss this in the next chapter. So we'll be keeping it till here in this particular chapter, that is the dual nature of matter and radiation. So let us deal with some problems based on Broglie wavelength or the wave nature of light. So we are beginning with the first problem. Calculate the momentum and Broglie wavelength of the electron accelerated through a potential difference of 56 volt. So in the problem it is given that the accelerated through a potential difference of 56 volt, and that is the only information that is provided to us. So based on the result which we have obtained for an electron, the Broglie wavelength for the electron can be written as 1.227 by root over V in voltage, and the result will be in nanometer. So if we solve this expression, we attain 1.227 by root over 56, and the value will be in nanometer. And on solving, we are getting a value that is equal to 0.1639 nanometer, which can be written up to 3 decimal places as 164 nanometer. So this is the wavelength corresponding to this Broglie wavelength when it is accelerated through a potential difference of 56 volt. In the next part, the problem is asking momentum. So if I write the formula for momentum, P is equal to h by lambda, so we can use the value of wavelength over here, and the value of h is 6.6 into 10 to the power minus 34 in SI unit, and the wavelength will be written in SI unit can be written as 164 into 10 to the power minus 9 meter, and the value will be in kg meter per second. So on solving this particular expression, we are attaining a value that is equal to 4.04 into 10 to the power minus 24 kg meter per second. So this is the way by which we solve this particular problem, in which the accelerating voltage is given along with the calculation of Broglie wavelength and momentum. Let us deal with the next problem. The next problem is stating what is the Broglie wavelength of a bullet of mass 0.040 kg traveling at the speed of 1 kilometer per second. So in this particular problem, we are beginning this way, that the mass of the object is given, that is 0.040 kg, this is bullet, which is traveling with 1 kilometer per second. So if it is traveling with 1 kilometer per second, we can write it as 1000 meter per second. And hence if I calculate the momentum associated with it, then it is equal to mu. So 0.040 kg into 1000 will give us the value of momentum that is equal to 40 kg meter per second. Now if I use the formulation for Broglie wavelength, lambda equal to h by p, so we can write it as h is equal to 6.6 10 to the power minus 34 upon p, that is 40 kg meter per second, and the value will be in meter. It is turning out to be 0.165 into 10 to the power minus 34 meter, which we can write it as 1.7 10 to the power minus 35 meter. So this is the answer for this particular problem, 1.7 into 10 to the power minus 35 meter, when a bullet is fired with a certain value of velocity. Let us deal with the next problem. One more illustration we are taking. For what kinetic energy of a neutron will the associated de Broglie wavelength be 1.40 into 10 to the power minus 10 meter? So unlike the previous two problems, this time the Broglie wavelength is given to us, and we are asked to calculate the kinetic energy associated with the neutron, whose Broglie wavelength is given to us. So if we consider this particular problem, the problem is stating that the Broglie wavelength associated with the neutron is 1.40 into 10 to the power minus 10 meter, and we already know that the mass of neutron is equal to 1.67 into 10 to the power of minus 27 kg. So based on this, these two ideas, we first of all approach in this way, that P is equal to h by lambda. So we are first of all calculating the value of momentum associated with this Broglie wavelength, and it is written as 6.6 into 10 to the power minus 34 upon the Broglie wavelength 1.40 into 10 to the power minus 10, and we attain a value that is equal to 4.71 into 10 to the power minus 24 kg meter per second. So this is the value of momentum associated with this particular Broglie wavelength. And if I write kinetic energy, so the value of kinetic energy can be written as P square by 2m. So if we do P square by 2m, so it is equal to 4.71 into 10 to the power minus 24 squared by twice of m, where m is equal to 1.67 into 10 to the power minus 27 kg. And this will give us the value of kinetic energy in joule. So on calculation we are getting a value that is equal to 6.68 into 10 to the power minus 21 joule. So this is the answer for this particular problem, in which using the Broglie wavelength and the mass of the neutron, we have calculated the kinetic energy associated with this particular neutron. Let us deal with one last illustration. The problem is asking what is the de Broglie wavelength of a nitrogen molecule in air at 300 Kelvin. Assume that the molecule is moving with the root mean square speed of molecule at this temperature. Atomic mass of nitrogen is given to us as 14.0076 U. So if we begin with this particular problem, so it is stating that the temperature of the nitrogen molecule T is given to us as equal to 300 Kelvin, and the atomic mass associated with nitrogen is equal to 14.0076 U. So from here I can say that therefore the mass of the nitrogen molecule which the problem is talking about, N2, is equal to twice of this value, so twice of Mn, and the value which we are getting is equal to 28.0152, and we are converting it in kg. So that is 1 U is equal to 1.66 into 10 to the power minus 27 kg. So we have converted it this value in kg. So this is the value of mass which we will be using. And now if I calculate the kinetic energy associated with this temperature, so I write kinetic energy as equal to 3 by 2 kT. And if I substitute the value, we have 3 by 2. K can be written as 1.38 into 10 to the power minus 23, and temperature is in Kelvin, that is 300 Kelvin. So the value is in joule. So we have the mass associated with it and the kinetic energy for this particular expression. So now if I write the equation for Broglie wavelength, so I'm not calculating these values. So if we calculate the value of Broglie wavelength, so lambda Broglie is equal to h by p, and it can be written as h upon root over 2 m kinetic energy. So now all we need to do is we need to put the value of h to mass which we have calculated, which is this one, and the kinetic energy which we have calculated, which is this one. So if we substitute this value, we will obtain the value for the Broglie wavelength. So let us do this. So we attain the value of Broglie wavelength as lambda Broglie can be written as h, that is 6.6 into 10 to the power minus 34 upon twice of mass. So twice of mass, that is 28.0152 into 1.66 into 10 to the power minus 27 into kinetic energy, that is 3 by 2 kT, 1.38 10 to the power minus 23 into 300. Maybe this expression is not looking very favorable to you, but this is the calculation that we need to do to calculate the Broglie wavelength associated with this particular nitrogen molecule. And on solving, we are attaining a value that is coming out to be 0.028 into 10 to the power minus 9 meter, and this is can be written as 0.028 nanometer. So these are the kinds of problems that are associated with Broglie wavelength.